All right, let's jump right in. In this deep dive, we're going to pull back the curtain on RusTs, a really interesting time series database written in Rust. We're going to explore the core design choices piece by piece.
So the big question is always this. If you were building a database from the ground up, specifically for stuff like IoT and real-time analytics, what decisions would you make? That's what this is all about. We're going to walk through the architecture so you have a solid mental model of the whole system before you even think about looking at the code. Okay, so just to set the stage, here are the highlights. We're talking serious performance thanks to things like columnar storage. It's compatible with the InfluxDB line protocol, which is a huge deal for migration. And you'll see this theme over and over: flexibility. You get tons of control over durability, compression, and scaling. These are the promises, and now we're going to see exactly how the architecture delivers on them.
So here's our game plan. We're just going to follow a piece of data on its journey. First, how it gets into the system, then where it's stored and compressed, how you get it back out with queries, and finally, how the whole thing scales up.
Okay, first up, the high-speed write path. A data point just hit the API. What happens now? What's the very first thing the database does to make sure that data is captured fast, but also safely? The design here is heavily inspired by LSM trees, and it's all about that critical balance between raw ingestion speed and the absolute guarantee that your data is never lost.
And it all happens in this very specific order for a reason. Data comes in. Step 1. Before anything else, it gets written to a log on disk for safety. That's the write-ahead log. Step 2. It's put into a super-fast in-memory table. And only when both of those things are done does the system turn back to the client and say, "Yep, got it." This sequence is absolutely key. And that write-ahead log, or WAL, is the system's insurance policy. It's durability first and foremost. Before data is even available for queries, it hits that simple log file on disk. So if the power cord gets kicked out or the server crashes, it doesn't matter. When it boots back up, RusTs can just replay that log and rebuild its in-memory state without losing a single write.
Now this is where it gets really cool. RusTs knows that not all data is created equal, so it lets you tune the trade-off between performance and safety. You can literally tell it, hey, for every single write, I need you to confirm it's physically on the disk. That's maximum safety. Or you can say, you know what, just let the operating system handle it. That gives you way higher throughput. It's not one size fits all. It's about giving you the knobs to dial in the behavior for your specific application.
Okay, so our data is safe in the wall and super fast to access in memory. But we can't just keep it in memory forever, right? That'd get expensive fast. So where does it go for the long haul? This brings us to the storage engine, and this is where the magic of efficiency really happens.
And to get why RusTs is so efficient, you first have to get your head around columnar storage. See, most databases store data in rows. But for analytics, that's not great. Columnar storage flips that on its head. It groups all the timestamps together in one block, all the temperature readings in another, and so on. This is a total game changer when your query is like, just give me the average temperature over the last month, because the database only has to read that one column.
So data in Rust at Tinos has this whole life cycle. It's born in the active tier, which is that in-memory table we talked about. After a while, it gets flushed down to the hot tier on disk, stored in those columnar files with a fast compression like LZ4, so recent data is still quick to query. Then, eventually, as it gets old, it can be moved to a cold tier, where it gets hit with a much stronger compression to save as much disk space as possible. And here is the secret sauce. RusTs doesn't just use some generic one-size-fits-all compression. It's smarter than that. It looks at the type of data. Timestamps are usually pretty regular, so they get a special delta encoding. Floating point numbers from sensors, they get gorilla compression. This is how you get these absolutely wild compression ratios, often squishing data down by 10 or 15 times. It makes a huge difference to your storage bill.
So we've stored our data super efficiently. That's half the battle. But now we've got to find it again. How do you query terabytes of this stuff and get an answer back fast enough to power a real-time dashboard?
Right, this is the million-dollar question for any time series database. You can't just scan all that data every time someone loads a graph. It would take forever. The answer, not surprisingly, comes from a clever indexing strategy, one that's a lot like how search engines work.
It's called an inverted tag index. So instead of going through every single data point to see if it's from, say, server 01, the index is like the index at the back of a book. It has an entry for server 01 that just points directly to all the time series that have that tag. This lets RusTs instantly jump to the exact data it needs, skipping terabytes of irrelevant stuff,
It's a massive shortcut.
And the technology that powers that index is a really cool data structure called a roaring bitmap. You can think of it as a ridiculously fast way to keep track of lists of numbers. So when your query asks for data where region equals US East and service equals API, RusTs just takes the two bitmaps for those tags and does a near instantaneous AND operation to find the exact set of series that match both.
Now, how you talk to the database matters a lot. You can use a standard HTTP API, which is easy and flexible, but if you're pulling back tons of data, that text-based overhead adds up. For maximum speed, Rust supports the PostgreSQL wire protocol. Because it's a binary protocol, it cuts out a huge amount of parsing and processing, making queries something like 5 to 15 times faster.
Awesome. So the system is blazing fast on one server. But let's be real, who runs on just one server anymore? What happens when your workload gets too big for a single machine? This is where we get into clustering.
To spread the load, RusTs uses a technique called sharding, which just means splitting the data across multiple nodes. But here's the clever part. It doesn't just randomly chop up your data. You get to choose the strategy. If your dashboards are always looking at the last hour of data, sharding by time is probably your best bet. If you just want to spread things out evenly, you shard by series. This lets you optimize how data is placed to match how you query it. And of course, if one of those nodes goes down, you don't want to lose its data. That's where replication comes in. And just like with the wall, you get to choose your trade-off. If you're handling financial transactions, you need absolute certainty, so you use sync mode. If you're just blasting a fire hose of metrics where losing one isn't the end of the world, async gives you the lowest latency. It's all about aligning the system's guarantees with what your app actually needs. So if there's one thing to take away from all this, it's that there is no single best setting. The entire design of Rust is a masterclass in balancing trade-offs. Every choice, from the write-ahead log to the replication mode, is a deliberate, configurable knob that lets you balance performance, durability, and efficiency for your specific workload.
Look, understanding why these architectural choices were made helps you reason about any complex system, not just this one. And that leaves us with a final thought to take back to your own work. Take a look at your data stack. Where is that critical bottleneck? Where are you trading performance for durability, or vice versa? And is it the right trade for you?